Good evening, ladies and gentlemen. Thank you so much for coming. St. John's, one of the permanent aspects of its program is the dialogue between ancients and moderns. And it's particularly difficult to do justice to the moderns, especially because so much is unfolding in our own time. That's why it's a very special treat today to have Daryl Haggard, an alumna and a friend of the college for many years, that's going to speak to us tonight about one of the most exciting topics in contemporary physics, black holes. The history of this goes far back, actually, into the 18th century. The theologian John Mitchell and Pierre-Simon Laplace both speculated about the possibility, but it wasn't really until the 20th century and the advent of general relativity that it became possible to imagine and really go into depth in the possibility that there might be a collapsed body of such density that light itself might not be able to escape from it. Some of the crucial calculations were carried out by Oppenheimer and Volkoff. So to mention our American, even local and New Mexican Faustus, this is perhaps the greatest piece of physics that he ever did, although he didn't recognize it at the time. The concept was very, very controversial. Einstein himself tried to refute the possibility of such a thing in a paper written not long after Oppenheimer and Volkoff. And I remember as a freshman hearing John Wheeler speak, one of the proponents, who is usually credited with the name black holes, although that was actually invented by a student and Wheeler saw the beauty and the wit of the title and took it up. But then, in the middle 60s, the concept was highly controversial, and I remember hearing as many people doubting that it could be possible that the laws of physics could be followed so exactly. Now, and that was at the occasion of the 50th anniversary of general relativity, now just approaching the 100th anniversary of Einstein's crucial paper, we're at a moment when black holes are everywhere, literally, at the center of our galaxy, in many forms that Professor Haggard is going to explain to you today. So just a word more about Professor Daryl Haggard. She went to St. John's and just celebrated her 30th reunion as a member of the class of 1995 and went on to get a PhD in astronomy at the University of Washington and has taught at McGill University and at various times at Amherst also, but is presently located at McGill. She's part of an amazing family that I would like to remember here today. Her father, Dean Haggard, whom I met, was a crucial figure in my life when I first came to the college and befriended me, and his amazing family, which I believe is present here in force this evening, and I would like to salute and recognize. So without any further ado, let me give you Into the Deep, Imaging Black Holes with Daryl Haggard.
Hello, everybody. Thank you so much for being here. I hope you can hear me in the back. And as is always the case, there are empty seats in the front. So if you are standing and uncomfortable, please come. I don't bite. I'm pretty nice. Just come on up. I originally did send in the title, Imaging Supermassive Black Holes, but somebody here at the college really didn't like that title and they changed it for me. So it's Imagining Supermassive Black Holes, and my brother Ben gave me a nice sort of mini insight into the difference between imagining and imaging. Imagining, we create the image in our minds and it's all invented out of whole cloth. And imaging, we really want the details right. So while I love imagining, tonight's lecture is really imaging. So for anybody that wanted to do the imagining part, I have a few moments in the lecture where I'll leave you to think your own thoughts, but mostly we're going to talk about imaging. So Peter mentioned the supermassive black hole in the center of the Milky Way galaxy. That's it, the orange donutty blob. We're going to really try to understand that image together tonight. The other parts of the image are a view of our central portions of our Milky Way galaxy, viewed at X-ray and infrared wavelengths. And we'll actually start tonight's lecture, after I do a little bit of introductory stuff, with a really cool video that is spectacular to me because it's all data. So I am an observational astronomer. I collect and interpret data from really a full suite of beautiful telescopes, amazing instruments that have been designed by brilliant minds all over the world. And it's amazing to me how much we can learn and how much we can see by linking together all the data that we've collected. Before I dive into talking about the Milky Way and the black hole that lives in it, let me just acknowledge we're going to spend a lot of time with our heads in the sky. So that's what we're doing here tonight. But we live on these lands and really enjoy the waters, especially on such a green and beautiful year as we've had here in New Mexico this year. McGill is on the sacred lands of the Haudenosaunee and Anishinaabe peoples. The closest group of people that are next to Montreal are the Ganawake folks. And I will tell you that my favorite thing about the Ganawake is that they have an amazing brewery. So if you ever come to Montreal, don't miss out on the Ganawake Brew Pub. They're fantastic. Here, my childhood home, of course, is Santa Fe, and St. John's is here on the unceded territorial lands of the Tewa and Tanos people, also known as the Pueblo Indians, or the Pueblo people of New Mexico. If you haven't gone out and explored the Pueblos, I really encourage you to do so. There are many different communities. They are incredible people, and so just I hope you'll go out and experience those peoples and learn about how they think about the sky, which is, I think, of great inspiration to a lot of us in astronomy. All right, people make up a lot of what I do. So nothing I show you tonight was done by me alone. We work in huge teams in astrophysics and in physics, and this is my team. They're beautiful. I cannot tell you how much they bring to my life and to my science. So all of my science is done with this incredible collection of young, brilliant scientists, and I just want to start by acknowledging the hard work that they do, and a lot of which, has brought us the things that I'll share with you tonight. But I also have my origins here. So a lot of my start is, due here to St. John's College. As you've already heard, my father was a professor here. We have alumni and family members. Those are a big Venn diagram of intersection in my family. And I actually got my first sort of kick toward doing astrophysics here during my junior year with Jack Stedman's seminar course. We were reading the Principia, which you'll see here featured. There it is. Probably not mine, but an equally battered version lives on my shelf still. And I was really excited. Jack explained to us that one of the cool things you can do when you start thinking about 2 and 3 body problems is you can envision scenarios where you use the solar system to slingshot stuff out into outer space. So as you may know, it's hard to launch satellites. It's hard to get out of our gravitational fields. It's particularly hard to explore the cosmos using physical structures. We mostly use light. But Jack explained to me that you can actually take a body, some sort of spaceship, and you can slingshot it around nearby planets. This is Venus here. And you can do these things called gravity assists, where you actually bump up its velocity by kind of dumping it into the potential well of a planet. And I thought this was just really awesome. So anybody who's excited about this is actually just a snapshot of a much bigger poster, and it shows you all the things we've ever launched off the surface of our Earth and how many gravity assists some of them require. And this is one of those gorgeous visualizations, and this is really where I started wanting to do astronomy. And the joke I always tell is that the first time I submitted a grant to the National Science Foundation, my mom sent me my junior high school poster, which was actually about what happens when galaxies collide. So she doesn't really buy this whole narrative. Apparently, I was interested in astronomy even earlier than that, but this is the way I remember it. So, St. John's brings us all sorts of different things as different people, but a lot of my love of science and appreciation for all of how we built it up and learned about science and physics in particular over, many generations of people is really due to the education that I had here. Okay. I think the next slide is a video. If it's not, I'll backtrack. But if it is the video, I think it is. It's an amazing thing because everything you're going to see in this video is all real. I'll try to narrate a little bit, but if you want to ooh or ah or just be wowed, please do that. I encourage you to make sounds. It's allowed. Okay, so Ooh, thank you. Okay, this is the Milky Way. You might recognize it. The kind of black weird stuff in the front is actually dust and gas that blocks our view. In a minute, you'll see a bunch more stars seem to appear. That's because we've shifted from optical wavelengths of light to infrared wavelengths of light, and infrared light penetrates that dust more successfully. And then X-ray, which is the very high energy end of the electromagnetic spectrum, is also successful at penetrating all that dust and gas. As we zoom in more, this video is going to actually sort of center on the position of the supermassive black hole that lives in the center of the Milky Way galaxy. And you'll see that there's hot, luminous material that emits X-rays. And using very amazing instruments called adaptive optics-enabled telescopes, we've actually also been able to take pictures of stars that are orbiting around. If you really look closely, some of you might see there was a little flashing light. Did anybody see there was a little thing going flick, 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 flick? That's actually flares from the supermassive black hole that lives in the center of the galaxy. But we really discovered it by tracing out those stars and watching them orbit around something that more or less looked like empty space. And then along came the Event Horizon Telescope, which is what I'll talk about mostly tonight, and gave us this amazing orange donut, which is in fact light being emitted from just outside the event horizon of the supermassive black hole that lives at the heart of our Milky Way galaxy. So you've just gone on a grand tour of our home, probing all the way into the central part of the galaxy to our supermassive black hole. It is affectionately known as Sagittarius A star, or Sag A star. The reason for that is it's if you were to go out into the night sky and look in the direction of the constellation Sagittarius, you will be looking toward the middle of our galaxy. And we name things based on a lot of these zodiacal namings that are old, ancient. The capital A means it's a bright source at radio wavelengths, and the star means it's at the center. So Sagittarius A star is in the direction of the constellation Sagittarius, and it's the central supermassive black hole that resides there. We were talking just before the lecture started, this supermassive black hole has 4 million times the mass of our sun. So astronomers deal in large numbers. It is difficult to give you those numbers in centimeters or miles or grams or kilograms, and so we tend to use relative units. We say it's this times the mass of our sun, or that many light years, or this times some other object that might be familiar, because that's just much more intuitive than using kilograms or centimeters. If at any point I use units that are strange, don't be shy to ask me in the Q&A what they mean. Okay, I'm going to give a very brief sort of mini physics lecture about black holes, and then we're going to go back to this idea about imaging them. So there are a lot of different ways to think about black holes. We're going to talk about a couple of them tonight. My personal favorite is to use this framework of an escape velocity because I find it very intuitive. So an escape velocity, in very simple terms, is the speed you need to send something at in order to escape the gravitational field of a body. So if you imagine Daryl taking a baseball and throwing it really hard, we all know what's going to happen. It's going to sail for a little while, and it's going to hit the ground. It's actually probably not even going to make it to the back of the room. I don't have a very strong throwing arm. But if I was Superwoman, Wonder Woman, Superman, whatever, some combination of those things, maybe I could throw that baseball really hard, and maybe I could throw it hard enough to put it into orbit. We know we can do this, right? This is what our telecommunications satellites do. We put them into orbit around our Earth. So if I can throw it really hard, I can almost hit that escape velocity. Then, if I want to send it out of the gravitational field of our planet, I have to exceed the escape velocity of our planet. So the simplest way to think about a black hole is to think about an object that is so dense and so massive that the escape velocity is faster than the speed of light. It exceeds the speed of light. And that means that light is trapped the same way as my baseball. So we're going to talk through a little bit about the implications of that. We're going to talk a teeny bit about the math of that, and then we're going to look at some images of black holes. So because light is trapped inside the black hole, the interior of black holes are invisible to us. We literally cannot receive any signals from beyond the event horizon. And this is a very interesting sort of domain for theoretical mathematics and theoretical physics to think about what happens to the stuff that you throw in, what happens to all of that information that went across that event horizon. But it is, from an observer's perspective, from an empiricist's perspective, it is lost, it is gone, it becomes invisible, we don't get it back. Black holes are actually very simple. The only things that matter are mass and spin. So how much mass does the black hole have? How rapidly is it rotating? Theoretically, they can have charge, which means they could have a positive or a negative charge. But astrophysically, when you put them into the world, when you put them into the universe, they are very quickly neutralized. And so we don't see charge as an observable of black holes in general. But theoretically, that's another property of a black hole. But that's just 3 properties. Those are 3 pretty simple things that characterize black holes almost entirely. Okay. This is the way that you might have heard about people talk about black holes, sort of bendings of space-time. So these space-time curvature, so maybe this is just a little graphic to help you think about how a different mass might alter the curvature of space-time. If it helps you, sometimes people like to use the idea of putting a bowling ball down on a trampoline. And you imagine that that changes the sort of topography, the sort of curvature of the trampoline. The thing that's different here is that you have to try to squint your brain and make that, this is the imagining part, everyone, squint your brain and make that 3-dimensional. It's not a 2-dimensional thing, it's a 3-dimensional thing. So the whole of space-time is curved. A white dwarf is a compact object, a neutron star, and a black hole. These are all different things that can happen when you squish mass down really into a very small volume. Another way to think about black holes is the escape velocity. We're going to talk a bit more about that. We're going to talk about these 2 concepts through a couple of different lenses tonight. And then the other 2 things that I've said already, but that you might have heard about black holes, is that they have an event horizon. And sometimes people talk about a singularity, and that's because this curvature in space-time for a black hole goes all the way to infinity. And that creates a kind of a mathematical singularity. It's like dividing by 0 or something like that. So you end up with a kind of a discontinuity in space-time at the position of a black hole. We're going to talk about escape velocity a little bit more. And this is where those of you who don't like algebra can just space out. Just think about something really nice that happened to you today. Do some of that visualization of black holes. It's only going to last 3 slides. But if you hate this stuff, just, be free to be you for a couple minutes. Okay, we're going to do just a little bit of math. Okay, escape velocity. So here's the equation, which might, it doesn't look that bad. So this is how fast you have to go to escape something, any object, with some big mass m and some radius r. And this is just the gravitational constant. So the 2 and the g are just constants. And the mass and the radius matter. Okay. You can actually calculate this number yourself using things that you might remember from one of your St. John's classes, maybe from high school, or maybe from some time bygone. The gravitational potential energy is that gravitational constant times the mass of the big thing, maybe the Earth, the mass of the little thing, maybe my baseball, divided by the radius of the big thing, say the radius of the Earth. So you can think about these as the gravitational constant, the mass of the Earth, Daryl's baseball, and the radius of the Earth. That's the gravitational potential energy. That's how much energy our Earth has to exert to hold our baseball down so it doesn't escape. The baseball is trying to escape. It's trying to get out of there. It might have some amount of kinetic energy. So the kinetic energy is 1/2 the mass of the little baseball and the square of its velocity. Hopefully, some of you have seen these things before. As I said, if this is not your jam, that's cool. We're not going to stay here very long. Just think about your day. Think about good things that happen to you, something you really love to eat, whatever. We're going to say that the escape velocity is more or less defined by the moment where these 2 things are just perfectly matched. I just have to slightly exceed that velocity to get out of the gravitational potential of whatever the big body is. So I can just set these things equal to one another to calculate the escape velocity. I've done that down here. And then I just did a little bit of scrambling around, a little bit of algebra to solve for the velocity, which is the same equation as we had up here. So hopefully that makes the escape velocity not seem so weird. It's not really all that fancy. And it turns out that these are the escape velocities. These are a few empirical numbers for numbery people. The escape velocity of our Earth is around 11 kilometers per second, so that's how fast Wonder Woman Daryl has to throw her baseball to get it off. In case that doesn't sound impressive to you, that's like 25,000 miles per hour. So you cannot actually drive your car that fast. There's no escaping. You need a lot of, rocket fuel in your fuselage to get off the Earth. Our sun has an escape velocity of around 600 kilometers per second. You can see the escape velocity increases with mass and decreases with radius. So when you go to one of these compact objects, something that is about the same mass as the sun, like a white dwarf star, but you squish it down much smaller, now you have a much higher escape velocity because you made this radius little, and that makes your escape velocity big. There's a square root, so it doesn't go up by a factor of 100, but it goes up by a factor of 10. Same with a neutron star. Here you have something that's a little more massive than our sun, but it's really scrunched down into something that's super, super tiny, and so you have a very high escape velocity. And so Peter was telling us at the beginning that people started to think about some concepts like this and realized, well, what about if I push this all the way to the limit? What if I take this velocity and I push it all the way to the fastest velocity we know, which is the speed of light? What does that tell us, maybe? And this is one of the frameworks that people used, in particular a guy named Schwarzschild, try to think about what would happen. Light would become trapped, and you would have this interesting thing where this escape velocity, this important quantity for any mass, was equivalent to the speed of light. And so this escape velocity, we just worked through how we get this mass. If I take this escape velocity and I set it equal to the speed of light, and once again just rearrange a little bit, you get this really important quantity known as the Schwarzschild radius. So you can see that this is the sort of radius, this is very similar to the event horizon radius that we use to define black holes. And you can see how simple this equation is. It varies with the mass of the object exclusively. Everything else in this equation is a constant. You have a 2, gravitational constant, and the speed of light, which is a constant. So the Schwarzschild radius depends on the mass of the black hole. You can make this a little more complicated, as I mentioned earlier, and have spin in there when you get into GR. But this is one of the very nice, simplistic ways of thinking about how you get a black hole. You create an object whose mass and radius demand that the escape velocity be larger than the speed of light. And here are some Schwarzschild radii. We're about to leave the math behind. But here, the mass of our sun is 1 solar mass, as you might imagine. If you took that mass and you scrunched it down to something about 3 kilometers in size, it would become a black hole. If you took something that was around a little over 3 solar masses, that would have a Schwarzschild radius of 10 kilometers. That object would be a black hole. And you can work your way on up to some of the big masses that we're going to talk about later in this lecture, 1 billion times the mass of the sun. It would have a Schwarzschild radius of around 3 times 10 to the 9, which is about 20 times the average distance between the Earth and the sun. That's known as an astronomical unit. Once again, we use a lot of relative units. So an astronomical unit is the average distance between our Earth and our sun, and this would be around 20 times that distance on average. And just stop and think about that for a second. That means that if I want a black hole that is 1 billion times the mass of our sun, I only have to fit that thing into something that is like inside the orbit of Pluto. Right? It would fit entirely in our solar system. That's a lot of mass smashed into a very small amount of space. Okay, just for perspective, if you took our sun and you made it into a black hole, it would actually fit between here and Atalaya. Okay, that's our whole sun squished down into something just about the size of, our local hiking area. So black holes are very, very, very dense and very small in the relative sense. One last point of comparison, just so that this is really driven home for everyone. If we took the Earth, we took your mom and your dad and your cousins and the oceans, the mountains and the trees, and we made them right around the size of a sugar cube, we'd all become a black hole. So black holes can be any size. They can be any mass. The thing that makes them unique is the combination of mass and radius. So it's a lot of mass in a really small space. Okay. So a lot of people then might be wondering, well, that's nice, Daryl, but you just crushed the sun down between here and Atalaya. What would actually happen if our sun collapsed into a black hole? So here's our solar system, here's our planets orbiting around a black hole. It'd be a very sad day for us. But it turns out that because of Kepler's laws, even if you did that, planets would still keep orbiting. So a very common misconception about black holes is that they go around sucking stuff in. I have an entire different lecture that I will not give you tonight that is called Black Holes Don't Suck. So they're not cosmic vacuum cleaners. There's no pressure difference. Nothing's getting sucked in. We would just continue orbiting around that black hole as long as the mass stays the same, and we'd all die a very cold death because there would be no radiation from our sun. It would be very sad, but we wouldn't get sucked in. So you might remember at the beginning I showed you stars orbiting around the supermassive black hole in the center of our Milky Way galaxy. Those stars are on stable orbits until something actually disrupts them. Maybe they give off a little radiation or something causes a disruption, but in the simplest scenario, they can just stay there in orbit forever. So black holes aren't, they're not shoving stuff into them, right? So this might make you wonder, how do they grow? This is a profound question. We actually don't know the answer completely. We have a lot of ideas, but growing black holes is actually tricky business. Okay, so if they don't suck, how do they grow? Two possible things are through gravitational radiation. I'm not going to talk about this tonight, but if people want to talk about it during the Q&A, I would be happy to. It turns out that much like that space-time curvature I showed you, you guys remember those plots where you've put the bowling ball on the trampoline? Now imagine instead those old-fashioned blenders where you've got two beaters going through your cake batter. Everybody kind of have a vision of that? All right, two black holes in space-time does that to space-time. So they take space-time and they kind of whip it up and make these ripples that we call gravitational waves. And those gravitational waves carry energy out of the system and cause these two black holes to approach one another closer and closer and closer until they actually merge. So you can build bigger black holes via gravitational radiation or gravitational waves, and you can just merge black holes together. There's a lot more to it than that, but that's one way that you can make them bigger over time. These kinds of radiation have been the gravitational radiation has been spectacularly discovered or verified. Just recently by the LIGO, Virgo, and Haggard collaborations, there was the 10-year anniversary of this very first detection just last week. So this is a very new area of discovery. It's very exciting, super interesting, but not tonight's lecture. I will just say that this discovery of gravitational waves won the Nobel Prize a few years back, and we just lost this wonderful physicist, Ray Weiss. He passed away, I think, 10 days ago, something close to that, 2 weeks. He was a spectacular human being, and this is a quote I love from him: "Every day is an interesting day." So if you're ever at a loss, just remember Ray. He was from the Bronx. He was like this, really kind of had a great attitude. He was just a loving person. And he designed those detectors with a bunch of university students in a homework assignment. So pretty not too shabby for that class. Okay, the other way you can grow black holes is by actually capturing mass. So I told you that black holes don't suck, but if you have some way of that black hole shedding energy, or stars or gas or things around the black hole shedding energy, it can fall in the same way meteorites and asteroids can fall down to our Earth. Our Earth is not sucking them in, they just fall down onto the surface of the Earth, sometimes through different radiative or other processes. And black holes also do a few interesting things. They can actually deflect and cause these orbits. This is a kind of funny stop-motion movie. You can see stars orbiting around Sagittarius A star. We saw that in our first video. And they also can deflect photons. They can actually bend and twist light around them, which is part of how we get these beautiful images from the Event Horizon Telescope. So we're going to talk more about that in our next segment. But this is another black hole. Peter mentioned that black holes have been in the zeitgeist recently. This is another black hole Nobel Prize that just happened a few years ago. This is a wonderful, beautiful colleague of mine, Andrea Getz, who I'm very proud to know, and who has worked really hard to bring people like me into this sort of scientific discovery space. Worked with a lot of female scientists, a lot of women over the years, and she's just brilliant herself. So these are images here, helpfully traced out by colored lines so you can figure out which stars are where. But these are stars orbiting around the supermassive black hole in the center of our galaxy. And this was one of the very first really convincing observations that confirmed that we have a supermassive black hole living right there in the center of the Milky Way. Okay. Last little physics bit, and then we're just going to talk about black hole images. So the last thing that you need to really understand the images that we take of the photons around black holes is called gravitational lensing. This is actually pretty familiar to every single person sitting in this audience wearing a pair of glasses. Your glasses are designed to bend light so it focuses at the right place in your eye. So much the way that physical lens redirects photons into your eye, masses in this curved space-time bend light and cause it to be deflected or moved, redirected as it passes around a massive object. This is known as gravitational lensing and comes as a result of space-time curvature. I told you we'd come back to that. So in general relativity, light follows the curvature of the space-time. So a light beam coming near to this would actually go down and maybe back out. I have a better picture of that in just a minute. But it will actually follow one of these lines that you're seeing in this grid, and so follow a different path if space-time is curved than it would if space-time was completely flat. So light is deflected, kind of like the lenses. I guess I'm not wearing my glasses, but if I were wearing them, so it makes me less nervous. I can't see all of you very well. It would be deflected by the lens of my glasses. Light can be deflected by any massive object distorting space-time. And this deflection angle, again, this should look really familiar now. This theta is the deflection angle, but these are the same properties, the same basic, simple properties that cause that space-time curvature and cause this deflection. The gravitational constant, the speed of light, the mass of the object, and how close you are to being aligned with that massive object. And again, here's one of these astronomical units that might be unfamiliar to people that don't think in astronomy all the time. This is known as an arc second. This will matter a little bit later. I think I have a little arc second primer. This is 360 degrees around a circle. If I take one of those degrees and I split it into 60, that's an arc minute. If I take one arc minute and I split it into 60, that is an arc second. So it's a very small fraction of a degree. Any circle has 360 degrees. And the images that we're going to look at, including the ones that you've already seen, are measured in micro arc seconds. So that is 1/1,000,000th of an arc second. So this is already a very tiny thing, and then we're going to talk about 1/1,000,000th of that thing. So people look at our black hole images and complain about how they look fuzzy. Let me just tell you, they are the crispest image you could possibly imagine. They are measured in units of micro arc seconds. It's just that we blow them up so that we can actually see them, and that makes them look fuzzy. It's not the black hole's fault. Okay, so back to black holes. I want to make sure you all know the units we're using. We're going to talk about these things a lot more in a minute. So we can also rewrite this deflection angle actually in terms of the same things. This time I'm not going to walk through the math. You guys can do it later if you're inspired. But we can rewrite this in terms of the same escape velocity we talked about before. So this deflection angle can be written as a ratio between the escape velocity for whatever object and the speed of light. And so you can see that if we have a black hole where the escape velocity is very close to the speed of light, the largest number we can get here is 2. So you can't deflect things like way, way, way off, but you can deflect them a little bit via having a mass kind of distorting the fabric of space-time. I told you I had a better, well, here's another picture, and then I have the better picture of what I was talking about before. So let's imagine you have a telescope at Earth. This is a really weird thing about gravitational lensing. Let's imagine that I have a black hole between my telescope and some star that's sitting in the background. And this black hole takes the light coming from this star and, like a lens, bends it a little bit. So the light that was coming from this star that should have missed us, that should have gone zoop that way, just in a straight line, actually gets slightly bent toward my telescope. That is what gravitational lensing does. But now I, as an observer, look up in the sky, and I'm accustomed to thinking of things looking like they're in a straight line. And so I see this light and project it back onto the sky, and I see it as being here. And so one of the weird things that gravitational lensing does is it actually creates lensed images. So I see this star maybe 3 times in this picture. And this really happens. We see this all the time. We can actually see beautiful things where I look straight through. Maybe this is a little above or below my black hole. So I look through, I see the star. And then I also see these lensed images that are the projection due to this gravitational lensing. So a really cool thing and a really important concept for understanding why our black hole images look the way they do. So in the case of a black hole, you not only have the ability to lens the stuff that's sitting way in the background, you also lens the stuff that's hot, the hot plasma very close to the black hole. So you can think of the black hole, if Daryl's the black hole, I was laughing at lunch today about dancing my thesis. Daryl will dance her thesis. Here I am. Here I'm a black hole. I have an accretion disk. I have material flowing because of angular momentum. It flattens out into a disk as it orbits around. And what the black hole gravitational lensing does is it actually takes the photons from behind me and twists them up to the top and twists them up to the bottom. So they're sort of just being pulled around me. And that makes my whole hot thing look like this cool halo. That's why you get a donut. So the photons and the mass might be all around me, but I'm kind of pulling it and twisting it into your line of sight. And that gives it this donut shape. I think here's this kind of nicer image of what gravitational lensing does. If you have a real star here, the path of that light comes to our telescope through space-time like this. I was trying to draw this with my laser pointer unsuccessfully earlier, but I also see this sort of interesting offset where I actually, if I were to follow a straight beam, might expect that star to be. So, in the case of black holes, so this is now a little image showing you photons, individual little packets of light interacting with the hypothetical black hole. And you can see some of the photons might have one simple kind of glancing encounter with the black hole, and that gives you a particular pattern of light. If you have a slightly more complicated, a slightly more influenced, you come closer to the black hole, you interact with it more, you actually get focused even more, and you get a much crisper image than that first one I showed you. The third one will show you an almost full orbit. Peter was talking about this at lunch too. So when you have your photons go almost all the way around the black hole, you get this thing called the photon ring, which is a perfectly crisp ring of photons that have been very strongly lensed by the black hole. But when we look at black hole images, all these different things are superposed on top of one another. So the outcome is that we see the photons that have been deflected just a little bit that make a more smeared out image, and the photons that have been deflected more by the black hole interacted with the black hole more, making a much crisper circular image. So this is what our theory tells us we're likely to see for black holes when we try to image them with our telescopes. Of course, the telescopes don't yet quite have this level of resolution. So we're working really hard on new experiments that might help us get at this really cool, crisp photon ring, but we're not quite there yet observationally. But at least you can start to see some of the features in the actual data in these simulations. And this is just a little kind of cool simulation video showing you, here's this mass. I was doing the dance of the mass orbiting around me. And you can kind of see how the black hole is actually taking and lensing the back of its accretion disk up over the top. So you're sort of seeing the light from behind the black hole, gravitationally lensed, and looks as if it's coming up over the top. And or from the bottom as we kind of went through that video. Okay, and you also see some lensing of starlight as well. So one of the things lensing does is kind of smear out images in the background. All right, I think that's it for the background. Is everybody ready to talk about the actual images? Groovy. Here you go. Okay, so this is the very first black hole image that was ever collected. The observations were taken in 2017. This is the black hole known as my M80, here we go, M87 star. You remember I told you the star means it's living in the middle of a galaxy. This is a supermassive black hole in the middle of the M87 galaxy, which, is in the middle of the Virgo cluster. It's a cluster of galaxies not so far from here in the direction of the constellation Virgo. And it also has a beautiful native Hawaiian name, which is Poehi, because one of the observatories that contributed a lot to these observations sits on the top of a sacred mountain known as Mauna Kea in Hawaii. And the name Poehi actually comes from their creation poem, which is called the Kumalipo, and it means something like the embellished darkness of creation. So this is a very beautiful name that the native Hawaiian community gave to this black hole when it was first announced in the very early days of the EHT. So we'll come back and talk a little bit more about what's going on here, but one of the things I want you all to know is that you already understand this image better than most people, because you see here that there's an event horizon, and you see that there is lensed emission coming from around the black hole. And if I told you the mass of this black hole, you could roughly tell me what its radius is, because you actually know how to calculate that. So it turns out this black hole fits inside the orbit of Mercury. It's very small, even though it has 4 times 10 to the 6, 4 million times the mass of our sun. And this emission is bright on the bottom, in part because that emission is moving toward us, where the emission along the accretions of the material is moving away from us on the back. That's known as the Doppler effect. Probably you all have seen that in other contexts as well. This is called Doppler boosting. So in this case, we actually think the geometry of this image is teaching us a lot about the accretion flow. One of the things that's really tricky about black holes is actually understanding how they're inclined to us, because as I kind of tried to describe, it doesn't really matter how the black hole's spinning. It's always going to give you this shadow. It's always going to give you this image, because it's always going to deflect the photons around it and look kind of circular. But it turns out, I'm not going to talk about this much, but M87 has a huge jet, an enormous outflow over 7 orders of magnitude, a huge jet that gives us some idea about the inclination of this black hole. And we think its spin axis is slightly tipped toward us, for what that's worth. Okay, here's the other one. So this is the other black hole that we've been able to image so far, and you saw this in the first video. This is our own Milky Way's black hole. This black hole, as I've already told you, is called Sagittarius A star. And this black hole sits, oh, I lied to you. I take it back. I lied. Everyone reverse in your mind for a minute. This black hole is much bigger than Sagittarius A star. This black hole has 6.5 billion times the mass of our sun, not 4 million. I lied. That was the next black hole. This one has 6.5 billion times the mass of our sun, and it doesn't fit in the order of Mercury. It does fit roughly out at the orbit of Pluto. Pardon, excuse me. This is the little one. 4-ish or so million times the mass of our sun, lives in our own Milky Way galaxy, does fit inside the orbit of Mercury. And so these two black holes, you might be kind of wondering, like, weird, Daryl, they look about the same on the sky. That's just a projection effect. It turns out we actually only have the ability right now to image 2 black holes. We're working on expanding that. But our whole experiment is somewhat limited by the size of our Earth. So these black holes are imaged by an experiment called the Event Horizon Telescope. This is actually not an individual telescope, but it's a bunch of instruments that are spread across the globe, and it uses the entire size of the Earth to build kind of a monster telescope. And it is actually the diameter of our Earth that limits how precise we can make our images. And that's because it relies on this technique called interferometry, where we use 2 different telescopes, and maybe we've got Sag A star out here, and we're looking at light from Sag A star, and we want to take an image using these 2 telescopes together, and to do that, we actually have to time these wave fronts. So each one of these peaks and valleys, we have to time them very precisely so we can correlate them across the different telescopes and make a synthetic image that actually has the spatial resolution that we can get from spreading them across the globe. So this is a little video of all of the different telescopes that actually make up the Event Horizon Telescope. They're all over the world. In Spain, across North America. Chile is a particularly exciting place to do astronomy. They have an entire national park dedicated to doing astrophysical observations. We have observatories in Arizona, Hawaii, as I've already mentioned, and even down at the South Pole. And so these telescopes are really incredible, and the people that know how to operate and bring us these data are also very incredible. And then I should also say we need a lot of computing time, and we also need a lot of really fantastic brains to make this happen. So this is our collaboration meeting in Berlin over the summer. These people also span the globe. So the telescopes are very international. The collaboration is very, very international. Okay, so back to the subject of these images. I was saying that the two black holes look very similar in size. I want to bring us back. You guys remember that definition of an arcsecond? You remember how it was a fraction of a fraction of a fraction of a degree? So these rings measure about 40 or 50 micro arcseconds across. So this is like if you took a human hair and you put it at the very back of the room and then you cut it up into a whole bunch of little pieces. That's the kind of resolution that we have of these black holes. And they look very similar in size, but it turns out that they're really, really different. And it's just that this one is very close and this one is very far. So you remember I said this had 6.5 billion times the mass of our sun. This had 4 million times the mass of our sun, but this one is about 1,000 times closer. And so that means in projection on the sky, they look like they're the same size, but they're not the same size at all. And we have, because people love to try to visualize these things, we're imagining now taking M87, which is that massive one, and yanking it from 55 million light years away to the same position as Sagittarius A star. So if you could take that big black hole and drag it in to the position of our black hole, you can see that they are not the same size, okay? This one is huge. This one is very cute and small. So just when you look at these images, just know that part of what you're seeing is a projection image. This one's much, much, much further away. The other thing that's unique and different about these two black holes is that it turns out that how they vary, how they change in time is actually also deeply tied to how much mass they have. So you can see Sagittarius A star, our supermassive black hole, whipping around. Believe it or not, this movie is moving. So in a relative sense, the variability time scale for M87, the more massive one, is much longer. It changes over much longer periods of time than our own black hole, Sagittarius A star. This may seem like a trivial thing, but it turns out that when you want to take a picture of a black hole and it's like bobbing around and jumping and changing all the time, it's really hard. And that is what we have with Sag A star. Over the course of one night, it varies all over the place. So if you look at the Sag A star image and feel like it looks a little bit more smudgy, it's because it is. It's because that black hole actually changes while we're trying to take a picture of it. It's like your toddler or your, irritating, I don't know what, mother. My mother hates having her photo taken. She's constantly getting out of the line of sight. So these variability timescales can make the images of these black holes really challenging. And one of the things we have to do to take pictures of Sag A star is actually do a kind of an averaging process. So we have imperfect data. If you imagine those telescopes that I showed you spread across the globe, and you think for a second about a mirror, and imagine that you only had little bits of silver at a few points on that mirror, and you were trying to reconstruct your reflection. So think about it, you've got just, some sort of gray matter, and then you've got a few little reflective points. You could make some pretty good guesses about what your reflection might look like. Maybe there's some hair, maybe there's a jawline, 2 eyes, but you could reconstruct that image a lot of different ways because you're missing a lot of information. That's more or less what we have in the case of Sagittarius A star. Because it's changing while we're trying to take the picture, it makes it very hard. We only have very limited information. So we take all the physics we know, we stuff it into a whole bunch of different ways of reconstructing the image, and then we average it all together. So here comes another movie of what that looks like. So just look at these little patches. These images that you're seeing here are all true to the data. They all match the data, but you've reconstructed the image differently in many, many, many different cases. And then we average all of these different possible realizations of that image together to create the image that you see and that we've shared with you all to say this is the image of our black hole. We don't do this arbitrarily. Some of the young people in the audience I even talked to today are thinking a lot about machine learning and artificial intelligence, which for those of you that have worked with these tools before know they're very good at classification. Maybe not so good at creative writing, but pretty good at classification. So we use machine learning techniques to create classes of different images. And then we use these different classes to kind of build what we thought was the most likely black hole. So it's not a straight average, it's a weighted average based on how many images fell into each one of these classes. And because machine learning is fairly new to all of us, we also tortured that beautiful group of people and made them do it all by eye also. So humans classified all of these images, and machines classified all these images, and we found a lot of concordance between those different things. And this is where you can kind of see this image had, this blue bar worth of number of images. This particular one had this pink bar, this one had this green bar, and this was a less likely but not impossible realization of the image. And then we average this kind of a weighted average of these different possible images. So sometimes you hear, and we as scientists, I think it is healthy to critique the things that we do, and sometimes you hear, ooh, it's a synthetic image, as if we just invented it, as if we imagined it. But indeed, we did not just invent or imagine it. We used what we thought were our best understanding of physics to fill in the gaps of our knowledge and average that together to get this particular black hole image. And so this is very close to the end of my talk here. I've had a couple of Nobel Prizes up here in my talk over the course of the lecture. You might notice that in 2024, AI won the Nobel Prize in Physics, which many of us were a little bit puzzled by, but I think there's some real physics in there. But my colleagues really lost their minds when this was the press conference, because it may not scream out to you, but all of my colleagues were like, why did they put the black hole upside down? They were so upset. And so here is a colleague's tweet where they just flipped all the Nobel laureates upside down in order to have their revenge. So anyway, now all of you know that the bottom of the black hole from our perspective is the bright part, because that's the stuff moving towards you. Like, really, seriously, come on. Anyway, I will say that the frontier for this work, the thing that we're working on right now, so these now are two different images of the same black hole. So this is that really massive one that's far away, M87 star. The first image was collected in 2017, the second one in 2018, and you might see that things have changed a little. So this is really interesting. We're starting to now think about how do we understand the dynamical properties of these? How do we make movies of the black holes instead of just single static images? And we're very excited to start getting time series. We just had a paper out as a collaboration a couple of days ago, that is showing 2017, 2018, and now 2021. And these kind of spirally overlays that you see on there is actually mapping out the magnetic structure, which I didn't talk about tonight, but is another important part of the material outside the black hole. And you can see it looks like it's sort of swirling in one way, sort of swirling in a different way, and then swirling back in another way. This is way, way more complicated than we expected it to be. We thought this black hole was going to do something nice and tidy and just do some nice, clean orbiting thing, and it turns out that even this more tame, less variable black hole has a lot more diversity in its images and in its magnetic structures than we expected. And I'm sharing this with you just to let you know that this is really the tip of the iceberg. We only started doing this a few years ago. We're very excited, but there's a lot that we don't know. And one of the things that's cool about astrophysics is that it's a real discovery science. We go out, we do our best to design an experiment, and a lot of times we find things we didn't expect. And that's really cool, because then we learn new things. We challenge our theories, we challenge our minds to come up with what might explain the things that we're seeing. And because our models are so incomplete, we're often surprised. And I will say, the last pitch, and then I think it's time for Q&A, is that this black hole, M87 star, we have an entire campaign for the first time ever, starting in 2016, 2026, next year. We're going to look at it every month for 3 or 4 months, and sometimes even multiple times in a month, to try to build you something more convincingly connected than why did it do that, and then that, and then that, which is basically the status of things right now. Like, whoa, why did it do that? And what we'd like to do is to have more frequent imaging to try to see if we can link together how the behaviors and how the material around the black hole is changing in time. And with that, I will happily take questions.